Okay everyone, I'm going to show you how to do the Snell's Law PhET simulation. This is going to be our last lab, I believe, of the marking period, which is exciting, but I think also a little bit sad. In class we would usually use the simulation, so this isn't so much a modification, but it is much cooler when you can do it with real lasers in class, but we can't really do that right now, so instead we're going to do this. So at this point, you've learned a little bit about Snell's Law. You've had a lesson on it. So I'm just going to go through how to do this lab and show you how to do it. All right, so first off, name. Make sure you put your name. The learning goals is mostly we're going to be making graphs, and you're going to make predictions about what you think is going to happen. And then you're going to, it's just the scientific method. You're going to analyze your conclusions and whatnot. So to start off, you're going to do theory, the definition, so you can use your textbook or the internet. So what is a medium? Absolute index of refraction. What is refraction? What's normal? Not like normal, like, oh, that guy's normal or not. I mean like normal in terms of Snell's Law, because that does mean something very specific. It's a more sophisticated word for, well, I don't want to give it away. But once you get into higher level mathematics, instead of using the word perpendicular, they like to use normal. Anyway, I digress. So angle of incidence, angle of refraction. So for the first experiment is going to be the dependence of angle of refraction on the angle of incidence. So the laser falls from air to a transparent medium. So it says, what do we expect to happen to the angle of refraction as the index of refraction of the transparent medium increases? And explain. So I really like this picture here because I think it shows very clearly what we're going to be doing. So for instance, you are not going to be changing this angle. So it says set angle of incidence at 50 degrees and leave it unchanged. For this experiment, you are not going to change that. And I'll show you I'll show you right now. So let me open up, there we go. All right, so this is the simulation. We push play and it'll open. You're going to use introduction, bending of light. And here you'll see a laser. We can turn the laser on. Ta-da! You'll see a little faint reflection. You'll see that it's refracting. We're going to use the protractor. I'm going to measure this out. And we are going to set it to 50 degrees, right? That's what it said. Let me look. Yes, we're going to set it to 50 degrees. So I don't want to show you what's going to happen. So, all right, so that's roughly 50 degrees. You're going to put it exactly on 50 degrees. And then you're not going to change this part. See how you can change it to different things? You're going to keep that the same for this experiment. And then what you're going to do is you're going to vary this. So you can use, see this number here? You can change this. So what I would do, I'm going to turn the laser off again so you don't see what's going to happen. So I would probably start at like 1.1. You're going to have it start, you're going to measure the angle of refraction, and then maybe go up to 1.2, and then measure the angle of refraction, so on and so forth. Or, you could even go by like 0.05 increments if you'd rather. For your graph, it doesn't really matter. So that's the first experiment, and I'm going to put it back to water. Oops, just to show. And again, you're going to predict if I change the index of refraction, so the bottom part, if I change the material, is this angle going to get bigger, smaller, or the same? That's what you're trying to figure out. And you're going to make a prediction based off that. All right.